Hello students and welcome to another screencast with Mr. Swan. So what we're doing today is I have a little game for you guys to go play. It's called the Half-Life dating game. It's a nice little simulation to understand and get a little bit better at understanding the principles and almost even characteristics of Half-Life and getting really good with that idea. So we'll do that. Let's talk about your picture of the day first. And who doesn't like a nice Parasite picture of the day? So maybe the oldest ones. Maybe it's not totally confirmed yet, but it's probably a good chance. So let's go right through it. A 512 million year old bed of tube encrusted brachiopods in Yunnan, China offers compelling evidence of a parasite host relationship and possibly the oldest parasite ever. Parasites are usually small and soft bodied, so they do not usually fossilize well. So we just don't really have a lot. We kind of assume that they've been around pretty much since life has been around. But small things, soft bodies, don't really make good fossils. Shells really make good fossils, in particular, or hard body parts. Next paragraph. In a tan-covered outcropping in southern China, researchers discovered thousands of brachiopods clustered together. Hundreds of them had numerous tube-like tapered structures affixed to the exterior of shells. Those structures were arrayed like the spines of a fan, so that means they kind of like pointed out, kind of like that. With mouth-like parts positioned along the open edge of the shell. The tubes appeared only on brachiopods, never alone or associated with other fossils, suggesting that the organism could not survive on its own. The brachiopods were likely filter feeders, catching whatever food happened to drift into their open shells. So on the bottom picture, on the bottom left, you see like all these kind of like little spindles kind of coming out. That would help them kind of grab like a little food that the water would go through, and they work its way down. And those white tube things on the shell on the bottom left-hand picture as well. I kind of move my mouse pretty close to it, like over here. Those are what they're talking about, the parasites. So as the food would probably come down, maybe the parasites would go and kind of grab it if they could. So the brachiopods were likely filter feeders, catching whatever food happened to drift into their open shells. Scientists hypothesized that these tubes might have snatched food from the edge of the shell before the brachiopod could eat it. So that's kind of like the guess and what they did to kind of like look and see if they could test that theory. To test this theory, tube-covered brachiopods should be lighter than their tube-free brethren, since they're getting less food. Researchers estimated the mass of brachiopods with and without tubes, finding that the tube-free brachiopods were almost always heavier than their tube-laden brethren, although the number of tubes didn't have any effect. So if they had some tubes on there, then they were going to be a little bit smaller in size, probably because they had less food. And some neat fossil evidence, and kind of a clever idea to actually weigh the mass of the brachiopod, which I I'm not sure if I would have thought about that. Brachiopods, a nice little shell creature, still around, been around for like 500 million years. They haven't really changed too much, and they're still going strong, actually, over in the ocean. So let's go right on over to your assignment for today, which is this one. Oh, before I go back on, I got an email asking like what was I talking about for Half-Life in regards to COVID. So I'm gonna bring that up as well. I figured maybe we could kind of like talk a little bit about the Half-Life again. So just a kind of a quick refresher. And Half-Life is all about taking the half of the remaining amount. So I did not open those notes, so let's do that real quick. It's coming down right to the end. This is our third to last lesson together. Can't even believe it. Time flies. So decay and half-life. So it's about half of whatever is actually there. So if you have half of a substance, and that substance has to have a certain number of atoms like in it. So let's say like 100, and if you went through one half-life, that original substance would go from 100 down to 50, and that the 50 would have changed to something else. There's still like 100 total atoms in there, but 50 of them now are something new. And the amount of time that takes is considered to be one half-life. And if it goes through another half-life, it goes down and reduces by half again. So it doesn't just drop from 100 to 50, and then from 50 to 0. It goes from 100 to 50 to 25, and then it gets progressively less and goes half and half. So for COVID, I'll put this link in there for you as well, so you can probably read it. It's probably a little bit too hard on the screen. They kind of do something very similar. They're trying to take a look at like how long this virus can last on different objects, and so they actually have they use a little bit of logs. I'm not sure if you've done that yet in math, and some different kind of techniques to do this. But in short, that's really what the first part is talking about, like what they really want to do. Second paragraph is talking about like how they would actually measure it, and how they were actually going to calculate it out. Third paragraph is really kind of going into the conditions of the actual surface. So like, what is the humidity? What is the temperature? And then it kind of goes into probably the meat of it, which is like right over here that you probably want to go read. Which was no infectious virus could be recovered from printing or tissue papers after about a 3-hour incubation. And so they estimated about the half-life of that was about a half an hour. So after I'd gone through about 6 half-lives, went from like however many viruses there are, let's say like 100, then one half-life would be 50, another half-life would be 25, another half-life would be like maybe around 12, another half-life maybe like around 6, then around 3, then around 1, and then gone. So after about 3 hours, you couldn't find it because the half-life would be about half an hour. That works for printing paper, that works for tissue paper. For wood and for cloth, by day 2, they could not actually find any more. And then what they found the virus lasts the best on are very, very smooth surfaces. So that'd be a glass, or stainless steel or plastic. It can actually last quite a long time. The amount for like stainless steel says day 7 is they couldn't find it, but it's still like slightly before then it would be like a really tiny amount. So like, would your chances of that be higher of getting it? No, it would be low because it'd be so little to begin with. But they just want people to know like it still technically could be there. And other things like your clothing, it's gone by day 2 completely, so it doesn't last on clothing very long. So just some good things to know. I will link this. This is like just like a one little page correspondence about their study, and I will put that in our classroom notes for you. So back onto your radioactive dating game. Is this the last graded assignment I had for you? I'm not 100% sure, but it might be. So really what this is, a nice little simulation that was made. It was over on FET. It was in Flash, but now it's over, and another group has made into HTML. So you guys will work on your Chromebooks and things like that. And it has 4 different tabs. In your assignment, we'll be go through all of them. But I figured I'll do like a run through of how each tab works. It's also kind of written in your simulation as well. So if you want to pause this and end this video now, that's fine with me. So if you want to continue on, then we'll continue on. So what this is the first part is like you're just kind of like adding atoms. And it'll start to autoplay as you kind of do it. So I'm just going to like empty out the bucket. There's a whole bunch in here. Right? And then if I was going to reset that and pause it, it kind of tells you like how much is carbon, how much is nitrogen after a certain amount of time has gone by. And if you play it and you kind of stop it at 1 half-life, pretty close, it's about, let's say about 40 to 60. So as I usually said before, like half-life is, it goes down by half. Again, this is all averaged out. It's all statistics, so it's not that number exactly every single time. So I'll try to stop this red one for you exactly right on there. Closer, 45, 54. Let's try it again. 48, 50. 47, 51, like numbers right up here. So I'm getting close to half and half. It won't be like that. You can do this over and over again. It will be close. It's never going to be exact. There's always a tiny bit of margin of error for these. And another thing I kind of want to point out is that you start all off as carbon, which is my little red atoms, and nitrogen is my little blue ones, and it goes from red over into blue. It's not like it starts on one part and one half. I take it back. It's not like it starts on just like the left side and just slowly has all its atoms just slowly change as it works over to the right. Which atoms go is like practically completely random. So sometimes the question is like, we kind of play this, kind of stop it. Like, why did that atom right there that was carbon change to nitrogen? How come that one didn't do it instead? Or this one, or this one? And the answer is nobody really knows. It's just kind of a neat thing that happens. There's no real great answer for it to explain like why one can last so much longer than another one. And it's always like a little bit confusing. It's because eventually you get down to like that last one. They're still ending, they're still ending, they're still ending. And then it's going to be either this one, the left one, or the right one. Which one? Turns out to be the left one. Why? Nobody really knows. Just a fun thing. So that's the first one, the half-life. I have a couple of questions for you to do that. My next one, if you add atoms into here, you slowly slide the bar this time. Kind of a similar idea. It changes from carbon over to nitrogen over time. And it makes that graph that you'll see like right over here. Right? So the carbon goes down, the amount of nitrogen goes back on up. After 1 half-life, it hits about 50-50. Right? After 2 half-lives, nitrogen's about 75% of the object now. Carbon is about 25%. You try it again. And that 50-50 line has shifted just a tinge. Still right about at that 1 half-life, but it's off just a little bit. Try it again. Now it's like a little bit more to left, not like a lot, but just like a little. So this is a point again, it's all averaged, right? So you have to do this multiple times before we kind of get to these numbers that we kind of agree upon. And you see like right here, it's like just like, it's actually way off. And then next one's now on the right side of the half-life line. So there's always like a tinge of margin of error for calculating half-life, and that's the reason why. The neat part is no matter what atoms you change it to, like if you change it from carbon and going to nitrogen, or like uranium going to lead, and then you play this, the graph stays the same, always. And technically, once you have one half-life graph, and you made it, just watching it go from 100% down to 0, and this one going from 0 up to 100%, right? It never changes. So you can use technically any atoms, any combination, would still the graph would look the same. The percentages over here on the side would be the same. The percentages that the parent element goes to, and at the same time the daughter element should go to, would always equal up to 100 and never changes. The little red lines in this case represent the amount of half-lives that have gone by. They don't change either. The only thing that changes is, depending on what atom you pick, the amount of time between half-lives. So this is uranium, it takes 4.5 billion years, but if you went down to my carbon one, same graph, it only takes about 5,700 or so. So that's the one thing that changes. So you seem to know what element you're working with to determine, like, what does one half-life mean in this case versus another one. Another thing you can do is not use so many atoms. Like this works really well. I talked about like if you use like a whole bunch and you have a whole bunch of things kind of going on. If you're trying to do like the average of a coin flip for like head and tails, and you only flip it once or twice, it's not really going to give you good averages, because same thing with this one. If you just have like a couple atoms and you try to play it, it's not really going to line up as nicely, right? Like it didn't cross until here. You need a whole bunch of things before you get like a really good average, and then it will start to work out again. So that's just statistics, if you haven't taken that class yet, which I'm not sure if you do that right now, or maybe you've learned some a little bit later or earlier in your math career. But great class to go take whenever you're ready. All right, third tab, measurement. So now you're kind of using this stuff. So for carbon, just gonna pause this real quick. So here's your live tree. And if you look at it, the percentages will always be 100%, and so that means then it's alive. So they won't really find any nitrogen 14 in this, and the reason for that is because it's constantly taking in carbon from the atmosphere. It's continuously growing. Different elements are going in, different elements are going away, and it takes a while for that nitrogen to happen. So eventually it goes on, then you can kill the tree, the little button over here on the right. You play, and then the tree will die, and then it tips over, and then from here, this was calculating how long since the tree was grew, and it was at 100% carbon. And then up here, my mouse is, sure, maybe I could try to zoom this in, maybe make it a little better for you. Like here, then it starts to go down, so you have to wait for it to die before you can actually start to carbon date things, in this case. The reason why is because they can't take any more carbon in, because it's no longer alive. And you let it play, and then it will start to work its way down. My probe back on the tree, and that's why you can see that the amount of carbon 14 is changing over time, getting less and less and less. If I had the probe on there the entire time, that red line would have remained stable. So this line is now shifted a little bit because the tree was alive. So if you did carbon dated this tree, it would tell you that it's gone through about let's say 1.5 half-lives. That's pushing about like maybe like 8,000-ish years or so, but that doesn't tell you how long the tree actually lived for. And for that, well, that's what we cut it in half. If it's possible, and count the rings, then you can actually work its way all the way back. For rocks, if you try to carbon date a rock, let's say you have a volcano and you erupt it, then eventually you get like a little rock, right? And you cool the rock, so it becomes like a rock. And you wait, and you take a look at these carbon 14 meters, you will see nothing, because rocks don't usually have carbon 14 in them, but they usually do have uranium in them, right? And you can actually find a little bit of those uranium turning eventually over to lead, but it just takes a really long time for it to happen. If we found a rock that was 50% uranium and 50% lead, in this case, the uranium isotopes that we're working with, uranium-238, then that means that rock is about 4.5 billion years. It'd be around since the beginning of Earth. We usually do not find those. If you do, let me know. Same thing if you actually go back to the tree. Plant your tree, and you search the tree for uranium, which is the uranium probe. You might notice that there's no uranium in them. because usually you don't find uranium in trees. That's the only reason why. Moving on to the last tab is called the dating game. This is for you to kind of start to work out some of the math for this. So like, let's do a couple together. So like your tree, put the probe over the tree. It says, what is the age of this tree? Well, it has 97.4% carbon-14 in them. 97.4%, you take your little slider, you bring it over to 97.4. The graph is already done for you. I am very close. And it says 221. Type in 221. Check estimate, and you get this nice little green check when you're correct. If you try to do this with uranium for that tree, you minus 0. So that just means it doesn't work. It means you have to use something else. If you went down and tried to do, let's say, this fish, and you try to use carbon-14, you'll see that it says 0. That means it died way too long ago. Too many carbon half-lives that would have gone by. You're just not going to find any more in it. So that means you have to use something else. If you try to use uranium, it's also going to say 0 because the fish probably, hopefully, did not eat uranium. So we use some custom isotopes. They have one on here. So like a half-life, instead of 5,700 for carbon, they have 100,000. And it goes up to 1 million. Still not there, so you gotta need one a little bit older. And then 10 million has about 14% left. Or if you did one that has 100 million, has about 82% left. You can use either or. You just drag your slider. For this one, it says 82%. 82.4. Very close to my 82.3. And it says 28, about 28 million. So if you type in 28 MY, it's not going to work. So what went wrong? So you have to actually type in the full number. So 28 actual million. Then you get to work. So you can't actually type in the MY. Program just can't handle it. And this works for anything. You can actually indate the wood that makes up your house. Fun fact. So go ahead through and date a couple of those ones. I put it on the sheet. And the major goal of this, I know as always, is to finish the work and turn it in. But to get a better understanding of how half-life works. And once you kind of get the idea of like what it is, about the atoms are slowly changing over time into a different atom, then you need to kind of work out that mostly half-life is just math. And then it's actually kind of the same math, and nothing really ever changes as long as you know how long the half-life of that atom is. And then this kind of helps you slide it around. So when you actually date things actually truly out in the field and you find these cool things, you never get something that's exactly 50%, or exactly 25. It's so rare. These are actual more realistic when you actually get something and it says, 83.9% or 99.1%, because the wood in your house probably isn't that old, right? Or a fossil you find like maybe just out in a field, really high carbon amounts. So it probably means more recent. So that's more realistic. So this will kind of hopefully help you understand that idea. If you have any trouble, as always, send me an email, and that's about all I have for you today. So hopefully you're doing well, and I'll see you next time. Goodbye.